And then we have y dash bar. So y dash bar is the vertical distance from your neutral axis to a center that gave you area above point of contact. So y dash bar, it is the vertical distance from your neutral axis to center of the shape that gave you the area above or below point in question. So when you say y dash bar is the vertical distance from neutral axis to the center of the shape that gave you area below or above point of contact, we say, let's say you are at C, right? Calculating shear stress at C. So in calculating shear stress at C, this will be your area above point of contact plus this area. So in calculating C, your y dash bar will start from here to this center of this shape. So it will be y dash bar 1 and then plus this area of BA. So also y dash bar will be from the neutral axis to the center of your y dash bar. And then on our formula we have IXX. So IXX, it's the moment of inertia. So IXX is BD cubed over 12 plus AC squared. So your answer must be in millimeter to the power 4 or meters to the power 4. So to calculate y dash bar or C, it's the same way. It's y lower minus y bar. So it's y lower minus y bar. So C, so y dash bar and C, they are one and the same thing. Also C, it is the distance from it is the vertical distance from the neutral axis to the center of the shape that gave you area above or below point in question. So the simplest way you calculate it, it's y lower minus your y bar for that shape. So if you get a negative answer, you treat that value as an absolute value. So you ignore that negative should you get a negative answer. And then we have B. B is the horizontal distance. B is the horizontal distance. So again, let's say you're calculating shear stress at C. So C, when calculating shear stress at C, so B will be this whole distance. So that will be UB. So when you're calculating shear stress at A, this whole distance, this whole horizontal distance will be UB. Same thing when calculating shear stress at B, this will be the whole distance. This is the whole horizontal distance. So this will be UB. Let's say you are given a structure like this, a hollow section. So this is point A. and then this is point B, and then you have your neutral axis here, point C and point D. So when calculating shear stress at A, and this B in your formula will be this whole distance, right? Same thing when calculating shear stress at B, B will be this whole distance. So when you're calculating shear stress at C, we can see here that there is a hollow section. So this is a hollow section. So in this area, it's a hollow. There's a hole here. So when calculating shear stress at C, this will be your B on this side plus this B on this side. So that is this B from this formula means this is the horizontal distance from the point in question. When calculating shear stress at A, this will be your total B. Calculating shear stress at B, this whole distance will be your total D. But when calculating shear stress at C, this will be your B plus this B to get the B that you will use in this formula. So these are all the variables you'll use to calculate your shear stress. So there are steps of calculations that you must be able to follow in order to calculate shear stress at any point in question. So here we're going to have steps of calculation. So the first thing you do, it is to calculate y lower. So y lower is equal to sum of area times y bar all over sum of area, of which is equal to millimeters if your dimensions are in millimeters, or meters if your dimensions are in meters. So you calculate y lower and y upper. So y upper will be the total distance minus y lower. So y upper will be the total distance, that is the height of your section. So total height of your section minus y lower. Second thing you do, you calculate your Ixx. So Ixx is equal to b d cubed over 12 plus ac squared. So again, it must be in millimeters to the power 4 or meters to the power 4. And then, so as I've mentioned previously, that C is equal to y lower minus y bar. So you'll see this formula, how it applies when we're doing an example. And then the third thing, after you've calculated these two, it's where you calculate your shear stress at any point in question. So the first thing you do, you calculate your y lower and your y upper using this formula, that is sum of area times y bar all over sum of areas. Then once you got your y lower, calculate your y up. Second thing you do, you calculate Ixx. So Ixx is equal to BD cubed over 12 plus AC squared. So C is y lower minus y bar. After you've calculated these two, then you can calculate shear stress at any point in question. So we're gonna do a quick example to show you how to calculate shear stress at any point in question. So let's say we are given a structure of this nature. So let's say this is 500 millimeters, and then this is 600. Let's make this 400, and then this width, let's also make it 500, and then iwebo, let's make it 100 millimeters, and then S will be, let's say, 50 kilonewtons. So let's say this is point A, point B, point C, and then you have your neutral axis, of which will be point D, here point E, and point F. So we will calculate shear stress at point A, B, C, D, E, and F. So this is the formula that we use. So shear stress is equal to S times A times Y dash bar all over Ixx times OP. So your answer must be in newtons per millimeter squared or kilonewtons per square meter. So again, if you follow those steps of calculation, you say the first thing we calculate, it is y lower. So y lower is equal to sum of areas times y bar all over sum of areas. So we'll divide a structure, say, into shapes. So we'll name this shape 1, and then this shape 2, and then this will be shape 3. So we'll say sum of areas times y bar for each shape. So we'll have, for shape 1 area, it will be 500 times 400 times y bar. So since this is our first shape, so our y bar will start from the bottom to a center of this shape. So we all know that y bar, it is this vertical distance from the base of the structure to the center of the shape. So it will be, since we're dealing with shape 1, it will be 500 times 400 times 200, of which is y bar ka shape 1. So this is shape 1 plus shape 2. So area of shape 2, it's 100 by 600 times y bar of shape 2. So y bar of shape 2 will start from the bottom to a center of shape 2. So half of shape 2 is 600 plus this 400. No, half of 600 is 300 plus this 400. That will give us 700. That is shape 2. And then we're gonna plus shape 3. So shape 3 will be 500 times 500 times y bar. So y bar of shape 3, again, it will start from the bottom to a center of shape 3. So it will be 400 plus 600 plus 250. So y bar of shape 3, it's 1250 all over the sum of areas. So that means it would be sum of area of shape 1, shape 2, and shape 3. This is shape 3. So it would be 500 by 400 plus 100 times 600 plus 500 times 500 to get our y lower. So we'll just plug in these values on our calculators. 500 times 400. So we'll get 773.529 millimeters. So that is our y low. So to get our y upper, it will be the total distance. So the total distance is 1500 minus y lower. We get 726.471 millimeters. So we've got our y lower and our y up. So y lower, we got that it's 773.529, and then our y upper, we got it to be 726.471 millimeters. And then the second thing we must calculate, it is IXX. So this IXX, since we've divided our shapes, our shape into 3 shapes, so we're going to calculate IXX for shape 1, IXX for shape 2, and also IXX for shape 3. So this IXX, it is the sum of all these IXXs for shape 1, shape 2, and shape 3. So you're gonna calculate Ixx, of which is BD cubed over 12 plus AC squared. So you can calculate for shape 1. So for shape 1, B will be 500 times depth, of which will be 400 cubed over 12 plus area, of which is 500 times 400 times C squared. So we said C squared is equal to Y lower minus OY bar. So C, we'll call it C1, is equal to Y lower. We got our Y lower to be 773.529 minus Y bar. So Y bar of shape 1, we got it to be 200. So your C1, C1 will be 773.529 minus 200, of which will give us 573.529 squared. And then you get your answer. So 500 times 400 cubed over 12 plus 500 times 400 times 573.529 squared, we get 6.845 times 10 to the power 10 millimeters to the power of 4. And then calculate Ixx for shape 2. So for shape 2, B will be 100 by UD 600 cubed over 12 plus AC area, it's 100 times 600 times C. So C2 will be 773.529 minus Y bar of shape 2. So Y bar of shape 2, we got it to be 700. So minus 700, which will give us 73.529 squared. And then you punch all those values in your calculator to get your answer. So it's 100 times 600 to the power cubed over 12 plus 100 times 600 times 73.529 squared. We get 2.124 times 10 to the power 9 millimeter to the power 4. You do the same thing for shape 3. Shape 3, our B will be 500 and then D will be 500 cubed over 12 plus area, of which would be 500 times 500 times C3. So C3 again, it's y lower minus y up. So y lower is 773.529 minus y bar of shape 3. We got it to be 1,250. 1,250. So 773.529 minus 1,250. So we get 476.471 squared. So we can see here which we're gonna get a negative answer. So you just ignore that negative and treat that value as an absolute value. So we have positive 476.471. Punch those values again in your calculator to get your answer. So we'll have 500 times 500 to the power cubed all over 12 plus 500 times 500 times 476.471 squared. We get 6.196 times 10 to the power 10 millimeter to the power of 4. So we have calculated Ixx for shape 1, shape 2, and shape 3. So at the end, we'll get sum of Ixx, of which will be the Ixx that we're going to use in our formula to calculate shear stress. So we'll add Ixx of shape 1, 6.845 to the power 10 plus 2.124 to the power 9 plus 6.196 to the power of 10. So our Ixx is equal to 132.534 times 10 to the power of 9 millimeter to the power of 4. So we have done our second step of calculating Ixx. That means we can go now and calculate shear stress at any point in question. So our point in question is point A, point B, point C, point D, point E, and point F. So let's calculate shear stress at point A. So we know the formula. So shear stress is equal to S times area times y dash bar all over Ixx times OP. So shear stress at A will be shear. So our shear we are given as 50 kilonewtons. So as I've mentioned, if your dimensions are in millimeters, you must convert your shear into newtons millimeter. So newtons millimeter, go with millimeter. If you're using kilonewtons, then you must go with meters. So we'll have 50 times 10 to the power of 3 times area. So we said area is the area below or above point in question. So we said it is the area above point in question if we are still above the neutral axis. So once we are below the neutral axis, we will be looking at the area below point in question. So since A is above the neutral axis, so it will be the area above point in question. So this is A. So A, the area above point in question is 0. So A will be 0 times y dash bar, of which also be 0, all over our IXX. So our IXX was 132.534 times 10 to the power 9 times OP. So as I've explained previously, that B, it is the horizontal distance from the point in question. So A is our point in question, so that means B will be this whole distance. So this will be OP. So our B in this case will be 500. So the answer in the end will be 0, because we have 0 and all this is multiplication. So it will be 0 newtons a millimeter squared. And then we calculate shear stress at B. So shear stress at B, again, it will be 50 times 10 to the power 3 times the area above point in question. So we are at B, so we have the area above point in question. So the area above point in question will be 500 by 500 times y dash bar. So again, y dash bar, it is the distance from the neutral axis to the center of the shape that gave you the area above point in contact. So we're going to have y dash bar. So y dash bar, same thing, y lower minus y bar.